Let's talk about equipotential and field lines. We're going to first start with a definition, then we're going to move on to conceptualization, then run through a few examples, and finally finish up with an object lesson. To define a few terms, let's start with equipotential. Equipotential is a surface or line composed of points all at the same potential. Before we can understand what that means completely, we need to break down potential, or in other words, potential energy. Potential energy is energy that is stored in an object because of its position, or in relationship to other objects. A good example of potential energy is a hill with a ball perched on top. This ball has a lot of potential energy. We can make it static by putting a blockade between it and the ground, but gravity is still pulling on this ball. Since this ball is not moving, it is not having any work done. And so we can say that it has a lot of energy stored up. If we remove this, however, the ball can freely roll down the hill. And suddenly that potential energy turns into kinetic energy. Before we go any further, I just want to make sure that we know the relationship between voltage and potential energy. I've talked about potential energy a lot already. And voltage is actually pretty much just potential energy times charge. Or you can look at it this way, voltage is potential energy per unit charge. Let's move to conceptualization. To do so, let's look at a few equations. We know that potential energy equals voltage times charge. We also know that voltage equals K times charge over R. We can further our understanding with defining work as negative potential energy. Let's break it down with a point charge. Let's call it a positive point charge with electric field lines directing outward, going from positive to negative. These electric field lines put a force on particles depending on how far away they are from the point charge. Because these points have different radiuses to that point charge, we can say that this static electric field causes different voltages at these 2 points, because we know that voltage is equal to charge over the radius, and the only thing that's changing is this radius. So let's go into some examples. I've drawn for you a capacitor here and a point charge example, just to illustrate the fact that you can have a surface that is an equipotential or a line, like I have drawn for you here. So let's break down this example in the capacitor. We have point A and point B. So at point A, we're going to plug that in to this equation here. I've defined voltage as electric field times the distance, or the voltage equaling the electric field times radius. So in this example, we have point A that's 1 meter away from this plate, and I'm going to define the electric field across this space as 10 kilovolts over meters. So if we plug that in and we multiply by the radius, we get the voltage of A is 10 kilovolts. Now let's do B. So you're going to get a difference in voltage, right? Equaling 30 kilovolts. However, if we were to look at 2 different points, if we plug that into the equation, we realize that voltage A equals 10 kilovolt, and so does voltage B. So do we have a change in voltage? No. And that is how you define an equipotential line. No change in voltage. Let's do an example with a point charge now. We can use the same equation that we used above with electric field times the distance away from the point charge. Here we have point A and point B, and they're the same distance from that point charge, but in different locations. So if we plug in point A, let's define electric field as 2. Same thing with B. We can look at the change in voltage, which is equal to voltage B minus voltage A, and we realize that we get no change in voltage. Now to draw in the equipotential lines. We can draw points on all of these electric fields 2 meters away. And now, connect the points. We have now a perpendicular line to these electric fields, and along this field, we have no change in voltage. You can also conclude that if you have no change in voltage, if this equals 0, you also have no work. So if you have a particle that moves along this line, it takes no work to move this particle along equipotential field lines. Okay, so since we've defined it, we've conceptualized it, and we've looked at an example, let's just sum up what we've talked about so far before we move on to the object lesson. We know that equipotential is a surface or line where all the points have the same potential. We use different equations to illustrate this in different situations. Next, we need to stress that equipotential field lines need to be perpendicular to the electric field lines. Electric field line, equipotential line. Next, we need to know that electric field lines create a force that creates the potential energy difference. We discussed gravity. An electric field acts a lot like a gravitational force. Lastly, if there is no change in voltage, you know that you have found an equipotential field line. So as you can see, we have a visualization of what is actually happening in an equipotential field. So we have our charge in the middle, and we have 2 test charges that are getting pulled in by this charge. Okay, so when you have them at different radiuses and you let them go, I don't know if you could tell, but the one that was closer hit the center ball first. But if you have them at the same radius, even though they're on different sides, if you let them go, they'll hit the ball at the same exact time. So since they hit at the same time, we can conclude that they have the same potential energy, and that is representing an equipotential field line. So all along here, or anywhere, honestly, that's the same radius from the charge is an equipotential line. Same voltage all the way around.